So when it comes to actually graphing these, they're a little weird because they're the only function where you plug in y to solve for x. Every function you've really ever done in any algebra class, you've plugged in an x value to get y. For the log functions, we're going to plug in a y value and get an x. So the only thing I want to make sure you guys don't get confused on, because my brain does it too sometimes, is because you're used to plugging in x to get y, and you're doing it backwards, your brain tells you that that first point you plugged in was x, when really it's the y coordinate. So you'll graph yx instead of xy just accidentally. So just be cautious of that. But I'm going to just plug in some values. It really doesn't matter what you guys start with, but I always like to start with one more than whatever is being added to your function. So like right now, this is really log base 4 of x plus 0. So I always like to plug in whatever that value is. And then I also try to always do one more value than that. So if we plug in 0 and 1, and then we'll plug in 2. So I like to always plug in at least the value that it is, one more point than that, and then maybe if you have room on your graph, one more. So if we plug in 0, so 0 equals log base 4 of x. So if there's nothing being added or subtracted on the right hand side, you can start right away by undoing the log. So you guys know when we undo a log, that becomes exponential. So this will become 4 to the 0 power equals logs gone x. Anything to the 0 power is 1. So 1 equals x. I like to do my table first, and then once my table is done, plug in my points. So let's do 1 now. So 1 equals log base 4 of x. 4 to the first, logs gone, equals x. So 4 equals x. And then the last one we're going to plug in is 2. So 2 equals log base 4 of x. Undo the log. It becomes 4 squared. Logs gone. So 16 equals x. So that one we won't be able to graph, but that's okay. So my vertical asymptote is really at that value on the inside of the parentheses that we solved for. So since there's nothing being added or subtracted, this particular vertical asymptote is just going to be at 0. So at x equals 0. The x-intercept, guys, is when you're solving for x and y is 0. So this right here is your x-intercept. So 1, 0. Domain and range. So range will always be negative to positive infinity. And domain will be from your vertical asymptote to positive infinity. And then I'll just plot my points. So 1, 0. And then 4, 1. So 1, 2, 3, 4, 1. And we won't worry about graphing 16, 2 because that's going to be off our graph. So we just draw our function in there. So really, guys, you just have to remember sort of what the shape of them is supposed to look like. So you can draw them, but then that will be it. And remember, there's nothing ever on that left-hand side. So we have log base 3 of x minus 2 plus 3. So again, I'm going to plug in this value and then just go up. So like if it were -2, like -2, I would plug in -2, -1. Like I would go up in values. That just helps to keep your exponents small because remember, when you want to do these, they turn into exponential equations. So we'll just start by, I can at least say already what my vertical asymptote is. So my vertical asymptote is actually at +2. It's going to be opposite this value in there. So there shouldn't be anything on the left-hand side of that asymptote. That means I know my domain will be from 2 to +infinity. And the range I know will always be negative to positive because vertically there are no restrictions where it ever stops going up and down in the y direction. So let's just go ahead and start by plugging in our first value, which is 3. So 3 equals log base 3 of x minus 2 plus 3. This one is going to be a little different because the log is not the only part over there on the right-hand side. If this log base 3 of x minus 2 were the only thing over there, you could undo the log right away, but it's not. We have to get rid of that plus 3. So the first step we take here is actually going to be to subtract 3. And this is why I always use that value, because what happens is then when you subtract it over, it becomes 0. So now you have 0 equals log base 3 of x minus 2. And now you can undo the log. So 3 to the 0 power equals x minus 2 because that undoes the log. 3 to the 0 power is 1. And then add the 2 over. And you'll get 3 equals x. So coincidentally, 3, 3. Okay, we'll try 4 now. So 4 equals log base 3 of x minus 2 plus 3. Again, when you subtract that 3, that gives you 1. So when you undo that log, it becomes 3 to the first power. So it keeps your numbers small. Equals x minus 2 because your log is now gone. Add the 2 over. So 3 plus 2 is 5. And now it does ask for the x-intercept, so maybe instead of 5, I'm actually going to plug in 0. We might not be able to graph it, we might be able to, but since we need that x-intercept, we have to plug it in anyway. So we need to plug in 0 for y. So I need to make some space here, so give me a second. Okay, so we'll plug in 0. So we'll subtract the 3 over and get negative 3 equals log base 3 x minus 2. Undo the log, so make this 3 to the negative third. Log's gone, x minus 2. So 3 to the negative third, guys, and remember, exponent rules. Moves that to the bottom and makes this 1 over 3 to the positive third. So that makes it 1/27. And then we have to add the 2 over. So the x-intercept will actually be 2 and 1/27. You can find that as a decimal if you want. So 1 divided by 27.04. So 2.04. So just a little past 2, and then we have 3, 3, and 5, 4. So your graph would look something like that. And you should probably try to at least get it through the point. But that's it. So when you guys are graphing logs, it's really a matter of plugging in y values and solving for x, and you actually end up undoing the logs. But the range will always be negative to positive infinity, and your domain is just going to be based off that vertical asymptote.